All right, first one is for partially synthetic data. And partially synthetic data refers to the synthetic data that not every attribute or variable is synthesized. Okay, and sometimes maybe you only want to, like, say, I think log income is sensitive, but I might not synthesize all of them. I might just synthesize some of them. So that will be considered as partially synthetic as well. Okay, so as long as something is unchanged, that's partially synthetic data. And that's, I think, the one that I've been talking about mostly. So the combining rules, okay, so for univariate estimate, we're going to use Q, and you can think of it as a population mean or a regression coefficient of a regression analysis if you're working with continuous case. So I think many of you, already know this, so bear with me. I just want to talk through the basics so we are on the same page. So Q is the point estimate of this, sorry, small q is the point estimate of the large Q from the original confidential data, and V is the variance estimate of Q. Okay, so we know that unless people like us, we pretend the data that we collect is confidential. Otherwise, yeah, except for the data disseminators, nobody else will be able to actually compute them. But since we're working in this area in a sense that we pretend, in the sense that the data that we have is confidential, we're trying to synthesize, provide synthetic data to increase the protection. So we assume that, well, we are able to compute it in some sense. So a key here, which might be, okay, typo, I should have the square here. Yeah. A key here is it's easy to get a little bit confused of what Q and V are. Okay, so just so you know, remember the original confidential data is a sample. Okay, and the Q is the population mean, which is unknown. Okay, so an intro stat or AP stat or some earlier statistics course that you took before, you probably know and hopefully remember that when you're working with a sample and you're trying to get a point estimate and variance estimate of the population parameter of interest, what do we do? If central limit theorem can be used, then we know that Q, the best estimate for Q, will be X bar, or like the sample mean, right? And then the best estimate for V is either sigma squared over n or S squared over n. Okay, so sigma is the true population standard deviation. Sometimes it's available, sometimes it's not. If it's not, you can use the sample sample standard deviation S to approximate. But don't forget, because of central limit theorem for the mean, what we have to be clear about is that when you estimate V, you have to divide that by n. Okay, so that's, hopefully everybody remembers why. By central limit theorem, we will need to, the standard error is not the standard deviation. So in practice, that's what we do when you're computing V. Okay, so keep that in mind, because it's easy to forget about that and then do all the work and then realize that your original confidence interval and synthetic confidence interval do not look alike at all. Things like that. Yeah, but it's easy to make that kind of mistakes. All right, so suppose we have m synthetic data sets. I'm using capital, boldface Z, Z1 to Zm to represent it. So for each synthetic data set Zi, let's have our Qi and Vi to be the values of Q and V each of the synthetic data sets. Okay, so combining rules, we call them combining rules because you still do the analysis on each of the synthetic data set. Okay, you get them, whatever, it might be a mean estimation, might be a regression estimation. You still do it at the synthetic data set level, but we get them, all of the estimates that we had, and then we combine them to produce valid inferences. So that's what combining rules is about. So that's why we still work at the synthetic data level, so we have this Qi and Vi. Okay? So once we have that, we can get this Q bar M, Em, and V bar M. Okay, so Q bar M, if you look at it, is just the mean, okay, mean of the Qi. That's reasonable, right? If the best guess, across the Qs will be the mean. So BM, if you look at the formulation here in equation 2, what is it? You have you can imagine you can have a sequence of the QI that you have, right? Q1 to QM, and then you just get the sample variance. That's what this expression is about, okay? And the last one, VM, V bar M here, is the variance, like mean of the variance estimate. Okay. So this different pieces here. So we have what? Q1, Q2 to QM, right? We have this, and we also have V1, V2, and VM. That's what we have once we do the analysis on each of the synthetic data sets. Okay, so what we're doing, equation 1, is that, well, our best guess of Q will just be the mean across the QIs. Okay, because we get the QI, which is the mean for each synthetic data set. And then if we want to average them out, take the best guess, it will just be Q bar M in this case. So that's what equation 1 is doing. And that will be the point estimate. Okay. You can think about it like there are different samples and you get the means from different sample means. The best guess is that. The key interesting thing here is equation 2. So I was saying that BM is really just looking at the sample variance across this Q's, right? Because this is what it is. You're taking the difference between each observation from its mean, take the square divided by m minus 1, that's how many you have, and then take the sum. So this is sample variance. So in a sense, what this combining rules, we're going to see the rules later, but what the 3 equations here are trying to collect from the synthetic data sets is that I not only want to know the point estimate, like I know the Q1, Q2, I not only want to know the average of the point estimate, I also want to know the variability across the point estimates. So that's what BM is trying to capture. Okay? And then this V bar M, well, we already have the variance estimate of each synthetic data set. That's V1, V2 until VM. And we want to get a sense of its average, so we take it. Okay, so that's what this 3 equations about. And then later you will see that they all come into play in terms of how to create valid inference for capital Q. In practice, these are not too difficult to compute, but the setup, I would admit is a little bit confusing or a little bit like complicated, so we just need to talk through them. So Q bar M, as we talked about, will be the point estimates of Q, and TP, which will be the variance estimate of Q bar M. So it is formulated in this way. Okay, so BM, we know that is the variability across the Q, right? So we're sort of doing that on average. So we do BM divided by M, and then plus the variability within each data set. Okay? So if you remember what we talked about in hierarchical modeling in 347, we're trying to say that the source of uncertainty comes from 2 places, right? Back then, the within group, what was it? Yeah, I think within group and between group, even in the hierarchical sense, right? Here, the same, because V bar M is what? V bar M is across the groups, right? Across data sets. Let me just use across. And then this is within. Is that right? My setup? So V bar M is the mean. So VI and QI, right? So BM is the variance of QI. So VI is what? VI is the variance of Q in each synthetic data, right? And we take the mean. So I think I got it reversed, right? What do y'all think? Confusing you? Let me just restart on here. If I look at this setup, I was saying that the variance estimate has 2 parts. We put them into 2 parts. My question for you is, which one? Yeah, I should have done this earlier. which one is the within and which one is between. When I say this is because when we think about uncertainty, because now we have multiple synthetic data sets, just like multiple groups, right? So my question for you is the uncertainty, which piece is the within data set uncertainty and which piece is the between data set uncertainty? Okay. So within will be like the estimates that you have for each synthetic data set. And then the between is when we compare across the synthetic data set. Okay, so let me do one more thing for you. The V bar M from before was what? Was 1 over M sum of I from 1 to M VI, right? And then the BM is the variance of QI, I from 1 to M. Okay. So I'm going to pause here so you can have a discussion with your neighbor. So again, my question or the setup here is that we know that this TP is being used as the variance estimate. Okay. What I'm saying is that the variance estimate, I mean the uncertainty in the variance estimate comes from two sources. Okay. One is about the variance or the variability or the uncertainty within each synthetic data. The other one is between the synthetic data sets. Because now we know, I mean, we want to estimate the mean. So we have the mean estimate in each of the synthetic data, right? And we also, so that mean estimate is going to have some variability because things change by synthetic data by synthetic data. But we also have within each synthetic data the variability, right? So I think I have everything. Yeah, so on the left I wrote the calculation for the V bar M and BM, and M is the number of synthetic data sets. So take some time and discuss with your neighbor which one you think is about the within, which one do you think is about between. Okay, so what do you think? So at the end of the day, we're trying to get estimate for Q, okay? So V bar M, and we know that VI, each of the VI is already the variance of Q in each synthetic data, right? And we take the average to get V bar M. BM, we know that we get the QI, the point estimate for each synthetic data first, and then we take the variance across them. So this one is looking at across, right, between synthetic data set, and we take the variance. So I would say this is between, and this is within. Does that make sense? Or we disagree?
Could you explain it again?
Or like, Kevin, you nodded, so.
Oh, so you want me to explain?
Yeah.
Okay, because the BM, the variance is like, it's not the variance of each QI, but it's like the variance of all the QIs together. And so that's like, I guess, makes sense that it's like across each group. You know what I mean? Like if you're taking the variance of each one, yeah, versus like aggregating it together and looking at like the comparison across. And so that's between the other ones.
Oh, there you go. Yeah. So the other one, we know that the VI is already the variance of Q in each synthetic data, right? So we get that. We take the mean. So that's the average within variance of each synthetic data. Okay. Yeah. So anyway, so I mean, whenever we think about variability or uncertainty, in this case, especially, we're trying to, the combining rules are really here to trying to capture all sorts of uncertainty in the most reasonable way. So it's probably, I mean, in fact, I think because the uncertainty comes from within each synthetic data set and between each synthetic data set, we should have a variance estimate as some kind of combination of the two. But I mean, the actual reason of why the form is in this equation 4, like I said, is more complicated, and there's theoretical background behind it. So I will post some reference so you can read about it if you want. But I mean, I think the essential part is to recognize that there are two sources of uncertainty, and we're trying to capture them into the variance estimate. All right, and then at the end of the day, once you have the variance estimate, you're able to use, in this case, a t-distribution. So this is again from central limit theorem and all that. They are giving you, they give you this, what is it, degrees of freedom for this t-distribution. It's complicated to compute. And once you get that, you're able to return a confidence interval. The confidence interval for Q, for capital Q, going to be centered, right, at the point estimate. And then it's going to be minus the t-score for that degrees of freedom multiplies with the standard deviation, right, and then plus that term. So this, again, goes back to, I think, intro stats or AP stats, the stuff that you learned. But at the end of the day, we're trying to combine the estimates that we have from multiple synthetic data sets, right? And we compute, if you remember, the point estimate and the variance estimate in each synthetic data first. So that's why you have the QI and BI, right? And then we try to summarize them in some way with this Q bar M, BM, and the B bar M. And then we're combining the two sources of variance or variability into the TP. And then once we get there, we are able to do a point estimate. So point estimate with Q bar M, and then the confidence interval estimate. All right, so this one will be straightforward. And synthetic C sample, again, it's partial synthesis. We only have log income to be synthesized, and log expenditure has not changed. Okay, so we have the synthetic one where we saved the data set earlier. Now we're doing multiple synthetic data sets, right? M equals to 20. I think that's what I asked you to do. So now I just wrote this like a loop, and I save every synthetic data set into one. I saved all synthetic data sets into a list of 20 elements here, and each element is data frame. Okay, so so this is very similar to before, except I try to make sure that I don't use the same seed every time, because otherwise, yeah, it's just complicated. So all right, so I think this part is okay. Like we generate 20 synthetic data sets and we save it to a list. You can save it to other form, whichever you want. And for this, we're gonna, of course, later, as you imagine, when we compute QI and BI, we're gonna like go into the list and then one by one to estimate that. Okay. All right, so the goal for us to get value inferences for the unknown mean of log income from 20 synthetic data sets. First step, compute QI and BI, the point estimate and the variance estimate of mean log income in each of the synthetic data sets. We have 20. So I started Q and V as NA, as vectors to start with, and then I write a loop from 1 to n, and then I go into the list to get each synthetic data first. So this is what I was talking about, that be super careful about, don't forget to divide by n, because this variance estimate is about Q, okay? Q is the unknown population mean. So we will have to do central limit theorem based method here. So when you get the variance, don't forget to divide it by n. Okay, so you get QV here, QIVI, and then you can get the Q bar M, BM, and B bar M. This is just mean, variance, mean of the various things that you have computed. And then you do the TP calculation and the VP. So this is just be careful, don't make mistakes, and then do it step by step. And lastly, we get the point estimate, which is Q bar M, right? And then also using the T, right? We talked about the T-score and all that. So don't forget, this is also easy to make mistake, that you can compute the T-score using the VP. That's fine, because that's degrees of freedom. Don't forget that you're using the QT function because you're trying to get the T-score. And then you're looking at because it's a 95% confidence interval, so we have two-sided. So we get that 0.975. It's easy to make a mistake to forget about taking the square root of TP, okay, because TP is the variance, right? When you're doing the confidence interval calculation, you're using your t-score multiplied with the standard deviation. Okay, so this is what we have here, and naturally you want to see, well, how close they are to the ones that you can get for the original. So I put the synthetic confidence interval on the top. To get the point estimate for the mean Q and then the 95% confidence from the original data, you are doing central limit theorem, essentially. okay? So you get the sample mean, okay? You get the sample standard deviation from the original data. So from there, you're able to, oh, not from there, sorry, the t-score, we know the degrees of freedom is n-1, just so you know. Refresh your memory when you're doing a sample. I mean, if you're using a sample to create a 95% confidence interval by central limit theorem or variation of it, because we're using t-distribution here, the degrees of freedom is n-1. So this is the sample mean from the original data, right? So that's the best we have. And then here I'm writing, so this is again, central limit theorem. Don't forget to use the standard deviation from the sample divided by square root n, okay? So this is the truth in some sense. Not the truth, because we never know the truth, what it is. The truth, because we are curious about the population mean. We never know what it is, okay? We have the original data to have a good estimate about it. And then we develop synthetic data based on the original data. But this kind of analysis is trying to get to the truth, which is unknown. Okay, that's why all of the central limit theorem, all that comes into play. Okay, so be careful where it comes into play, and then make sure that you're using the right thing. Okay, all right. So this one is, I think, good. And